Just a quick synopsis of what we're supposed to know about simple harmonic motion. Occurs when the net force is negative kx. If x is your position. So x is your position function, x of t. And your net force is constant multiple of that position. Okay, so negative constant multiples of the force is back toward the x equals 0 position, which is called the equilibrium position. So there's the whole condition. And of course your question was, what is simple harmonic motion? Again, it's not exactly how you phrased it. My answer was, when this occurs, it's your basic premise. You want to lock that in. You want to know what your basic premise is, because everything follows from that. And if you know how to follow it, well, net force is mass times acceleration, which is mass times second derivative position with respect to time. So you get this equation. And you don't know how to solve this. You haven't had a differential equations course, but common sense tells you that if the second derivative of a function is a negative multiple of itself, it better be a sine or a cosine. And it's better be then from the chain rule, x is going to have to be a sine or cosine, from which the chain rule through two derivatives gives you a negative k over m. So we let omega equal the square root of k over m, just to make it simple. When we originally did it, we used the k over m, and then we invoked the omega. So go back to the full development, but it all develops. And you can verify that this is a function, and I can tell you basic theorem in simple harmonic motion in differential equations is if you have a second order equation, one that involves second derivatives and stuff, you got to get, you basically solve it by doing something that's equivalent to two integrations. You can't do it with two integrations, but it's equivalent. Each integration gives you a constant. Well, there's a constant, there's a constant, and there's a constant. Okay? So for a given k and m, you can have any amplitude and any phi, but omega is determined. Okay? So now, once you've got this, of course, you can take derivatives and get these, and you got this picture, which is very important, very useful. Okay? That your x of t is a projection of this r vector, tip of which, or the vector is moving around such a way that this angle theta is an omega t plus phi, this argument. Okay? Meaning it's moving at constant rate around a circle, and you've seen things moving at they're more or less constant rates around circles at uniformly accelerated rates. That should be a familiar idea. It's also relevant to what we did there and what we're going to do with that. Okay? So you have this and you have this. Okay, so once you have this picture, it gives you something to hang on to. It's very useful. The velocity, I call Vx here, which is just a derivative of this, and the acceleration Ax being the derivative of this, are represented on this picture by just the projection onto the x-axis of this velocity vector. It gives you a vector down here that's about this long. And of course you can just project it up here. You've got your velocity vector, you've got your x direction. Here's your v sub x. And you have your acceleration vector, which is back toward the center. We've drawn it. I'm not going to mess up the picture by trying to squeeze it in. It's a small picture. Okay? But the same thing. You project that acceleration vector down here, you get a vector on the x-axis. And you can see that if you're here moving in this direction, that your acceleration vector is going to be here. Its projection here is going to go back this way. Okay? So the acceleration vector is back this way, which is good because the force has to be back this way, and the force is a mass times the acceleration. Okay, so all that stuff holds together with this picture, and you want to sort it out and use it when you look at problems. Okay, so simple problem, pendulum, amplitude 10 centimeters, mass 0.4 kilograms, net force -5 newtons per meter times x, and y'all did a good job. You know, I asked you to look at it and tell me what you got. It took you a minute to stare. You didn't stare, you were assembling things, and you came up with a good answer. So, A, of course, is the radius of this circle, which is the amplitude of motion. Amplitude of motion being the maximum distance from your equilibrium position, which occurs here and here. Okay? So we know A. So first of all, this, let's just start with this. A is the easiest thing to see, but this is most important. F net equals negative kx with k equal to 5 newtons per meter. Okay? So that's, we really want to focus on this. It's the most important thing you can see. And this relationship, omega equals square root of k over m, which is easy to understand if you do verify this differential equation. You see that that's what it has to be. The coefficient of t here has to be the square root of k over m in order to get this after two derivatives. That's really simple to see if you write it out. You want to lock onto that and remember that so you have all the connections. So, and we call that omega, okay? But it really is just the square root of k over m, omega shorthand. But omega has its own interpretation as the angular frequency of the motion. Okay, so anyhow, F net equals negative kx with k equals 5 newtons per meter. The mass is 0.4 kilograms. Well, that's 0.5 newtons per meter divided by kilograms, which is square root of 5. And newtons is kilogram meters per second squared divided by meters, all divided by kilograms. And when you sort that out, the kilogram divides a kilogram, the meter divides the meter. You have meters squared per second squared. And it's not meters squared per second squared because you don't have meters. So 0.5 seconds to the negative 2. Meter divides a meter, that's the only meter it's gone, right? Okay, so you get the square root of 5 seconds to the negative 1. Oh, it's 0.4 kilograms, isn't it? Man, I'm being careless today. Okay. Okay, it's 0.4 kilograms, so it's 20. No, really. 12.5. Okay. So this is 12.5 reciprocal seconds. Okay. Then the square root of 12.5 is about 3.5, about 3.5, maybe 3.6 reciprocal seconds. Okay. Square 3.5. Okay, so this, and this is interpreted as 3.6 radians over seconds. Because that is then going to be the angular frequency of the motion around here, since you're multiplying omega by t. Okay? Now, what's 3.6 radians per second? How big is 3.6 radians? We looked last week at a rotating thing, and we saw the radians about this, right? Of course, we know that pi radians is half a rotation, and 2 pi radians, of course, is a whole rotation. And we understand radians, I hope, so all that is pretty natural. So, 3.6 radians per second means a little more than half a cycle per second, okay? Half a circle on this reference circle and half of a cycle of this simple harmonic motion, okay? Which means that this thing is going to oscillate with a period of about 2 seconds, about 1,001, 1,002, 1,001, 1,002, okay? So we get all that out of this simple calculation, and it's critical, of course, to understanding what's going on with that pendulum, okay? Okay, well, there we have it. The other thing, of course, is the amplitude, which is the first thing you saw. Okay?
And you said the amplitude is equal to the furthest point on either side, so it's not just equal to the length of the pendulum?
No, it's related to the length of the pendulum. And we'll work out that relationship. We haven't worked it out yet. It's not necessarily a pendulum. It could be a mass on a spring.
Well, but you told us it was a pendulum.
Yeah, okay, well, it doesn't matter. From this, you can easily determine the length of the pendulum, if it's an ideal pendulum. But we haven't analyzed those forces yet, okay? And this could be a mass on a spring, okay? If I just change pendulum to mass on a spring, the whole thing still has that makes perfect sense, actually more sense with a mass on the spring. Remember the picture we have with the pendulum mass? Forces, right? You have a tension force, and you have the gravitational force, and you have this unbalanced component of the tension force, right? So this is your net force. Here's your tension force, and here's your gravitational force, which is the gravitational acceleration vector, okay? And we actually analyzed this by similar triangles. So this is why, this is this, and this tells you what the relationship is between the length of the pendulum and the force constant, okay? Just by similar triangles. So you're actually equipped to figure out what the length of this pendulum is, but I'm not going to ask you that right now. We'll just focus on how to use these equations of motion and the whole concept of simple harmonic motion, okay? We'll get to the specifics of the pendulum, which we've actually already worked out. It's been a little while. So what we're doing here is going to be enough of a chunk of information to deal with, okay? And that's just incidental. That's real easy if you know what similar triangles are and how to use them. If you don't, you need to learn. If you don't, it's because geometry has been dumbed out of the curriculum, which I keep saying. Okay? Okay, so anyhow, you got amplitude is 10 centimeters. So x of t equals 10 centimeters. And this is approximate times the cosine of 3.6 radians per second plus 5. And from that, you can easily get the velocity and acceleration function. So as soon as I write that down, those are automatic. Okay? You don't have to memorize these. Once you have this, you just take a couple of derivatives, and there it is. And that's not something you have any trouble with. Okay. Now, we still have this arbitrary phi. And A is also arbitrary. If I push the pendulum a little harder, what happens? The amplitude increases, right? Okay, well, put out the increased amplitude here, and I got an equation now for a pendulum that's got the same force constant, the same pendulum, but with a bigger amplitude. Okay? So the only thing I don't know is phi, and phi just really depends on where you choose to start your clock.
It's just the beginning angular position, right?
Yeah, so I want to draw that on the picture here, but I want to draw a bigger picture. And what you said is exactly right. So here's your circular model again. And here's your x-axis, which is the only one that matters, so I'm going to only draw it in. Okay? I mean, you could do it with the y-axis as well, but we're doing it with the x-axis. Okay? And in fact, you could do this with any straight line through the origin, which would also be a way of accommodating phi. But with this picture, let's just say that phi is here. Okay? Well, that means at t equals 0, where is this thing? Yeah. Okay. Since t is 0, it's cosine of omega t plus phi. At t equals 0, omega t is 0, you just got the phi. Okay? So x of t is 10 centimeters times the cosine of phi. X of, yes. Let's do this a little more clearly. Position is x of 0 is 10 centimeters times cosine of phi. Okay? So what that tells you is that right here is x of 0. Okay? And this is the t equals 0 picture. Now that's fine if you know phi. But what if we now say okay, suppose x of 0 equals 5 centimeters. What is phi? Well, I'm drawing a picture and you should too. Draw your reference circle picture. Here's your origin. The radius of the circle is 10 centimeters, right?
Yeah.
And x of 0 is 5 centimeters. So there it is, right? So what's phi? Where's phi on this picture? Now look at how x of 0 corresponds to phi in this picture. How does it correspond? Well, if you know phi, x of 0 is just a projection of this point at angle phi on the circle. Well, does that mean that phi is either this or this? Okay, so here is phi. Here's one possible phi. Right? But here's another one. So is it this one or is it this one? Well, if it's this one, then what can you say about the motion of the pendulum right after t equals 0? In what direction would the pendulum be moving?
Counterclockwise?
Your point on the circle is moving counterclockwise, assuming omega is positive, and that's the way we've written it. Okay? If you want to write omega as negative, it complicates things a little bit, so we usually don't do that. There'd be no good reason to. Okay? So we're moving counterclockwise here. I'm talking about where is the pendulum? What's the pendulum doing? Well, the pendulum position is the projection of the position on the circle. That's why the pendulum goes back and forth. Well, that's how the circle models the motion of the pendulum back and forth. The pendulum doesn't go back and forth because of some circle. It does because of Newton's laws and so forth. Okay? But the circle models it. The circle gives you a picture. It makes it easy to understand phi and its implications, and which phi it is. So, my question then is, if we're moving in the counterclockwise direction at this point, then what's the direction of pendulum motion? Is it toward the origin or away from?
Towards the origin?
Yeah. And this picture kind of represents what happens here. Now, if it's down here, then your velocity vector is this way, right? And when you project it up here, it gives you a vector in this direction. And it's obvious that if the pendulum is shadowing the motion of a reference point, at this point, if that reference point is moving this way, the pendulum has to move this way to keep up with it. Okay? Make sense?
It's rough.
Well, sort it out. Draw yourself some pictures. If I think of it, I'll throw something like that in the assignment, because pictures of, show me, show me 12 points around this circle. And show me where the pendulum is at each of those points. Then you begin to see where it's moving.
So what you're saying is, if it's the first phi, because the velocity vector is pointing towards the center of the circle, that's the direction it's moving, towards the equilibrium point?
Well, if it's this phi, it means that the thing is moving toward the equilibrium position, and moving back toward equilibrium. If it's here, it means the pendulum is at t equals 0 moving away from it. Okay?
Oh, it's because of the positive and negative. The top's positive, the bottom's negative. Yeah, the bottom.
Well, those are both positive phi's.
Well, they're positive phi's, but the second phi is in the negative half of the circle.
Negative half of the what?
Of the circle, it's beneath the x-axis.
That's it. Why don't you say negative half is to the left of the y-axis? There's no negative half of the circle.
All right, so that's not.
Yeah, I mean, you don't want to think that way, okay? You don't want to think that way. It's simply the circle is what it is, and if you're moving counterclockwise, which corresponds to a positive value of omega, then if you start at this point, it's because you're moving away from the origin at t equals 0. If you start at this point, you're moving toward the origin at t equals 0. So let me just draw a couple vectors. I mean, this would be your v of 0 now. Or this would be your v of 0. Okay? Well, in this case, your Vx of 0 is in this direction. Okay? Now, being in the negative direction doesn't mean it's going toward the equilibrium position, because it's moving in the negative direction over here. It's going away from equilibrium, right? So we want to really just talk about whether Vx is positive or negative. Okay? Now over here, of course you can project down here to Vx. and it's in the positive direction. I shouldn't have made that a vector. Okay? Or Vx is positive, right? I should have just said Vx is negative, Vx is positive. Okay? Motion is in the positive direction, Vx is positive. So I'm going to kind of cross out that statement. I didn't quite use the right words. It's motion that's in the positive direction. And here Vx, yep. It's negative. And here Vx is positive. Okay? So in order, telling you that x of 0 is 5 centimeters is insufficient information to know what phi is. You also have to know in what direction the thing's moving. Okay? And that's my point. Okay? So to determine the value of phi, for v of 0 is positive or negative. Then it's a simple matter of trigonometry. Okay? Now, to do the trigonometry, again, you know x of 0 is 10 centimeters times the cosine of phi, right? You know cosine of phi is then 0.5. So what does phi equal? It equals inverse cosine of 0.5, or what? Well, the inverse cosine of 0.5 is going to be this, right? But the cosine of this angle is also 0.5. So how does this angle correspond to this angle?
I know what it's called, I just can't think of it.
Well, okay, if this angle, well, you know the inverse cosine of 0.5 is, say, 60 degrees, or pi over 3 radians, okay? And we probably want to do it in radians, but you're used to thinking in degrees, okay? So, this equals then pi over 3. We don't have to write radians, but I'll write it, because radian is the default measure of angle. And I'll say that's 60 degrees, that's not a multiplication, you should understand the context. Okay, well, what would the other angle be? If this is 60 degrees, what's this angle?
300 degrees?
Well, 360 degrees minus 60, I'm saying how you're going to calculate it, right?
Yeah, I was trying to think of the term for,
Yeah, that's fine, that was a good answer, that I'm going to just focus on the right terminology, focus on a useful terminology. Well, that's 2 pi minus pi over 3. That is 360 degrees minus 60 degrees. And of course, that is 5 pi over 3. Okay? Now, and unfortunately, trigonometry classes have also been dumbed down, and you don't necessarily do a lot of this. I find that most people, even though they've had a second semester pre-calculus, they should do it, don't get this. Okay? They don't understand it. They don't understand how you write the infinite number of solutions to this equation. And some courses they do, yeah, but I find that in general it's not so. And we really need to upgrade our courses so it is. And that'll put us in a minority, especially among community colleges. But a minority among institutions of so-called higher education. Yeah, the truly good institutions do. You don't have to be an elite institute, just good institutions. There are institutions that teach, but institutions with high standards. Make sure people understand this. Okay? I mean, I learned it in high school.
Not John Battle.
Huh?
Not John Battle, in other words.
Well, yeah, I mean, public schools have a real problem
Oh, yeah.
with,
Everything.
Funding, everything.
well, funding, but it's really the demographics of students and the need to pass a lot of people that shouldn't even be in the course.
That's true.
Yeah.
Okay, well, community colleges are under a little pressure to do that too, although we don't admit it. Okay? We like to pretend that it's not true. And in some colleges, it's less true than others. This college is pretty good with that. Nobody directly tells us to dumb our courses down. Okay. And there are places where I guess nobody really directly, but it's strongly implied. Even though officially it's not so. That's. I might even be wrong about that. I've never been wrong about anything like that, but I might be. So you can't pick out an individual school, an individual school system, because it's pretty much the same everywhere. Okay. With some notable exceptions. Okay, so anyhow, there's the mathematics of it, but here's the picture of it. And take that picture all the way back to F net equals negative kx and try to understand every bit.